So, let us get started. So, today our goal is to learn about constraint satisfaction problems. We will talk about various examples of constraint satisfaction and the representation, which is very simple. Backtracking search, which is the paradigm to do search in constraint satisfaction. Then we will talk about how to improve the search by various heuristics, by the very important idea of reasoning or inference. We will talk about how different problem structures behave differently and what we can do about them, and we will touch on local search, although we will come back to local search more carefully in the context of logic. Okay, so, let us get started. A constraint satisfaction problem is one of the standard search problems, where instead of saying that state is a black box, we say that state is defined by variables and values. It is extremely simple. Like in the case, all of you are variables. Vishwajit is a variable, Kiran is a variable, Vipul is a variable, and your values are the chair numbers that you are sitting in. Kiran has value 15, Vishwajit has value 35, Vipul has value, now I have forgotten. So, the point is that in this way we can represent this class. Let us say we talk about n queens. Can we think of it as a variable value problem? Each variable would be, variable I would be queen's position in the ith column, and its value would be the position, right. If you think of n puzzle, you can again say tile position is a variable and its value is the actual position, etc., etc., etc. So, now if you think about it, most problems, many problems, you will be able to cast where you say that each state has a certain set of variables and each variable has a certain set of values, and a complete assignment to all the variables creates a final state. A complete assignment to all the variables creates a world state. And if we are doing local search, we will be doing local search in the world state. But if we are doing systematic search where we are adding one variable at a time, my node would be a partial assignment. Make sense? So, as the slide says, this is a simple example of a formal representation language. There is a spiel that I was giving earlier, and it allows for general purpose algorithms with more power than an atomic agent. That is very important, because in an atomic agent there was only state was only a number, there is only so much we can do. Now that state is more than a number, it is a set of variables and their values, we can do more, we can understand the structure of the state and perform better in our task. And for this particular set of slides, we will carefully look at the map of Australia, and we will try to solve the graph coloring problem or the map coloring problem. So, first of all, it will help to memorize this. We have 7 states in Australia: Western Australia on the west, Northern Territory on the top, South Australia in the middle on the south. Then here we have Queensland, New South Wales, Victoria, and Tasmania. Tasmania is an island, and these you have to sort of memorize. It will help to memorize because we will use that as a learning example. And let us say I give you 3 colors, red, blue and green, and I want you to color the map such that no 2 adjoining states have the same color. Okay? So, this is a very standard graph theory problem, and if we wanted to cast it as a constraint satisfaction problem, our variables would be 7: Western Australia, Northern Territory, Queensland, 1 variable for each state, like Australia state, not to be confused with AI state, and the domains would be red, blue, green. These are the 3 colors that we are allowed to use for coloring each variable. And then what will be the constraint? The constraint would be that Western Australia cannot be equal to Northern Territory, Northern Territory cannot be equal to Queensland, New South Wales cannot be equal to Victoria, and so on. These are in this case inequality constraints, which represent that 2 states which are adjoining to each other in the map cannot have the same value. Now, how do you represent this constraint is also interesting. You can represent this constraint with a simple inequality if the language allows it. Now, right, we have not really defined the constraint language, and different people study different sets of constraint languages, and this whole area is called constraint processing and so on. So, for it is a very active area of research. It is a full conference of its own. It is called CP, constraint processing. Okay, that is a very good conference. And but you may say that okay, not equal to is not part of my language, but enumerating the sets of possibilities is part of my language. Then I can say that my language can say that Western Australia, Northern Territory can take values from red green, red blue, green red, green blue, blue green, blue red, but not red red, blue blue, green green. So, they cannot be similar, but I enumerate all the possible correct pairs of values. And this is one possible solution to the problem. You know, you label color Western Australia red, Northern Territory green, South Australia blue, and so on and so forth, and this is my solution. The solution is a specific assignment to each variable such that all constraints are satisfied. Okay. Now, often people in constraint processing think of it as a constraint graph. In a constraint graph, each node is a variable and each edge determines whether there is a constraint between those two variables or not. This kind of a constraint graph is a binary constraint graph where each constraint relates at most two variables, and such constraint satisfaction problems are called binary CSPs. Now, you may say that binary CSP is too specific because each constraint is only between two variables, but in fact you can prove, or there are procedures which can convert a non-binary discrete CSP into a binary CSP. So, we can just think about studying binary CSPs and not worry about others. Of course, there is some lots of new variables need to be created, etc., etc. So, you know, there is a blow up, and so but in our course we will not talk about more than binary CSPs. If anything, we will talk about converting them to binary CSPs. That is about it. All the algorithms that we will study will be about constraints which are between two variables only. And a good general purpose search algorithm might quickly find that there are two sub problems in this problem. What are the two sub problems? What are the two sub problems? There are two independent sub problems. There are two connected components. Tasmania is in a different component and the other 6 are in a different component. And so, it really does not matter how we label Tasmania for the purpose of labeling the rest of the graph. So, we can actually convert it into two independent problems, solve each of those problems separately and come back. This would be fine. But this we would only be able to do if we looked at this constraint graph for some understanding of the structure of the problem. Now, we can think about the structure of the problem because each state variable is a node, not a state. And I hope you see that difference. Earlier, each state was a node. Now, a state has many variables, let us call them state variables. Each state variable is a node. So, we are operating in the world of state variables at this point, not in the world of states. Only then are we able to recognize that there are two independent subproblems. Now, CSPs come in many varieties. There are CSPs with finite domains, discrete variables. There are CSPs with infinite domains, discrete variables like integers or strings as solutions. There are CSPs with continuous variables. Okay. Many common real world problems are constraint satisfaction problems like job scheduling. I am a computer, I get many jobs, they all have ending times. So, I want to finish each job up to a certain before their end time, you know, it is a constraint satisfaction problem. I have many classes, I have many classrooms, I know which classes are happening at the same time, I know which class has how many students. Now, I want to do a scheduling such that we get this classroom and somebody else goes to the 6th floor to teach. Now, you can think about what are the complete set of assignments. Suppose I have a discrete CSP and I have n variables, and each variable has values which can be taken from a domain of size d, then how many complete assignments do I have? D to the n, right? The first variable can take d values, the second variable can take d values, the nth variable can take d values. So, we will have d to the power n complete assignments. So, if we could enumerate all the d to the power n assignments, then of course, we will be able to solve our problem really well, but of course, that is not possible because it is exponential. Similarly, different people study many different kinds of constraints. Do not label South Australia green. South Australia is a very, it does not like greenery, whatever be the reason, it is too close to water, I do not know. But let us say there is any constraint which says do not label South Australia green, then that will be represented as SA not equal to green. Then you have binary, those will be called unary constraints. Then you will have binary constraints that South Australia should not be equal to Western Australia. You will have higher order constraints like 3 or 4 variables come together and define a constraint. You may also have what is called soft constraints. Now, soft constraints need not be satisfied, but you get credit for satisfying them. It is like Vishwajit says, I like to sit in the front. Now, can I sit in the back? Yeah, I can sit in the back, but I would rather come early in the class and sit in the front. And then another person may have exactly the opposite constraint, or sitting in the front is too much pressure, I will sit at the back. Those are soft constraints. You do not always satisfy them, but you are happy satisfying them. Now, that if you have soft constraints in your problem, then that converts a constraint satisfaction problem into a constraint optimization problem. Why? Because now I have some constraints, I need to satisfy them, and I have some constraints, I may or may not satisfy them, but satisfying each constraint will give me some credit. So, I need to get maximum credit while satisfying all the constraints. That is a constraint optimization problem because of the maximum part. Many interesting problems that you study in real life can be thought of as constraint satisfaction problems. So, this is something that I am sure as children you have done. These are called crypt arithmetic puzzles, where if I give you 2 plus 2 equal to 4, where each symbol, each letter means a digit and a different digit, such that this particular sum is accurately satisfied. Well, what are my variables? T, W, O, F, U, R. But you will realize that if I want to actually put it as constraints, I will have to define 3 more variables. One will be the carry at second step, the carry at the third step, and the carry at the fourth step. Let us call them x1, x2, x3. What will be the domain? Domain will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. Now, what will be my constraints? So, one of my constraints would be that O plus O should be equal to what? It should be equal to R plus 10 times the carry, that is 10 x1, or W plus x1 should be equal to U plus 10 times x2. That will be one set of constraints. Another set of constraints would be all variables are different digits, and such a constraint is written in a syntactic sugar called all diff. You can always say T not equal to W, W not equal to O, T not equal to O, all pairwise not inequalities, but a syntactic sugar for this is all diff. We just remember this, everybody uses all diff, that all of these should be different. Okay. And then this is a constraint graph for it. Notice that now we have created these square nodes which represent a constraint, and multiple edges from variables can come in each constraint. Okay. But of course, we can always convert it into a binary CSP. So, let me end the introduction here to say that who teaches what class, which class is offered when, where is a class offered, how do I put in all the transistors into my configuration so that it can fit in the space given. I have a factory which employee comes at what time, such that all machines are running at all time, etc., etc., etc. These are all some version of constraint satisfaction problems.